Chapter 4, Section 21, Outlier Detection by MCD. This section explains a method for multivariate outlier detection using MCD to compensate for the weaknesses of the use of usual Mahalanobis distance. First, we review the limitations of using the ordinary Mahalanobis distance. Next, the procedure of MCD estimation is described. Then, I will show you how to detect outliers by MCD using Python. As we saw in the previous sections, to detect multivariate outliers, it is effective to use the Mahalanobis distance, which considers the variance of the variables and the correlations among the variables. However, there is a problem that the covariance matrix used to calculate the Mahalanobis distance is easily affected by outliers. Thus, if outliers are included, the variance may be overestimated, or the shape of the distribution may be greatly distorted. If the Mahalanobis distance is calculated based on this distorted covariance matrix, some outliers will be indistinguishable from normal data points. A solution to this problem is to calculate the Mahalanobis distance using a robust covariance matrix. Using a robust covariance matrix has the following advantages. First, it reduces the influence of outliers. It eliminates the problem of covariance matrices being distorted by outliers. Second, it improves the accuracy of outlier detection. It enables more accurate detection of true outliers. Third, it expands the range of application. More robust outlier detection is possible even when data does not perfectly follow a normal distribution. The popular methods for computing robust covariance matrices are the following. Minimum covariance determinant. It selects a subset of the data and calculates the covariance matrix with the smallest variance. It can stably estimate the variance covariance structure while ignoring outliers. Shrinkage covariance matrix. Shrinkage improves computational stability and reduces the effect of outliers by adding regularization to the estimated variance covariance matrix. It is especially suited for high-dimensional data. Robust location and covariance estimators. This method robustly estimates location vectors and variance covariance matrices using median and median absolute deviation, MAD. Each of these methods uses a different method of computing robust covariance matrices. However, they all have in common that, instead of a simple covariance matrix, a robust covariance matrix is used to compare Mahalanobis distances and detect outliers. Therefore, in the following, we will focus on the differences in the calculation of robust covariance matrices among these methods. In this section, we focus on MCD. Other methods will be covered in subsequent sections. Minimum covariance determinant is called MCD for short. MCD estimation is the process of minimizing the determinant of the covariance matrix of a subset so that it optimizes the determinant to be close to one that is computed on a dataset with no outliers. MCD estimation is implemented in the following steps. First, select about 50% to 75% of the data points in the dataset. Then, using the selected subset, calculate the determinant of the covariance matrix. This determinant is used as the objective function to be minimized. Next, for each data point in the subset, calculate the Mahalanobis distance from the center, including all data points outside the subset. Data points with significantly large Mahalanobis distances are then excluded as outlier candidates. Then, the subset is updated by adding the same number of data points from outside the subset as the data points excluded in the previous step. Next, calculate the determinant of the covariance matrix using the new subset. If the determinant is not smaller than before the update, reselect the data points to be added. If the determinant is smaller than before the update, the Mahalanobis distances of the data points in the updated subset are calculated as in step 3. Then, as in step 3, data points with significantly larger distances are excluded. It is important to know that if the determinant is not reduced, update the subset again, and then calculate the Mahalanobis distances and identify outliers. If the determinant does not get smaller, the subset is not considered to be moving in the optimal direction, so the data points of the subset are first selected again. Step 4 to step 6 are repeated until there are no more data points that can be considered outliers. Through this iteration, the values of the determinant of the covariance matrix converge. This is the process of minimizing the determinant of the covariance matrix of the subset, that is the objective function. Then, using the optimal subset, compute the covariance matrix and the mean vector that consists of means of each variable. These are the robust covariance matrix and the robust mean vector. Finally, using the robust covariance matrix and the robust mean vector, calculate the Mahalanobis distance for all data points, including those outside the subset, to identify outliers. Now, let's implement outlier detection by MCD using Python. In addition to NumPy, pandas, etc. that we usually use, we import distance to calculate the Mahalanobis distance. We also import a class for MCD estimation from scikit-learn. Besides, import a library for setting the threshold for outlier detection from scipy-stats. Here, we use the chi-square distribution for threshold setting, so we import chi2. Next, import a module to load the Wine Dataset from scikit-learn. Here, we will use the Wine Dataset provided by scikit-learn. Next, load the dataset. Load the Wine Dataset using load wine imported earlier. This data contains several columns of features representing chemical properties and a target column representing the type of wine. Using this code, we can convert a wine dataset into a pandas data frame named df_wine. Here, for simplicity, we use only two columns, alcohol and color intensity, for outlier detection. Let's store the two variables in the data frame named df. When we create a scatter plot, we can see that these two variables are correlated to some extent. First, let's detect outliers using the Mahalanobis distance calculated based on an ordinary covariance matrix without using MCD. I will implement this in the same way as in the previous section. I will not repeat the detailed explanation here. So, if you have not yet seen the previous section, please watch the video of the previous section. This part sets the threshold for outliers. When we assume that the data follows a normal distribution, the Mahalanobis distance follows a chi-squared distribution. Chi2 ppf 0.975 df equal to calculates the percent point function of the chi-squared distribution. that 0.975 specify the quantile corresponding to the 95% confidence interval. In this case, it specifies a data point corresponding to the upper 2.5% of the chi-square distribution. With this setting, data points with Mahalanobis distances that exceed the upper bound of the 95% confidence interval are considered outliers. df equal to specify the number of dimensions, that is, the degree of freedom of the data. Here, we use two variables, alcohol and color intensity, so the degree of freedom is 2. This code calculates the upper limit of the 95% confidence interval for the chi-square distribution with the degree of freedom of 2. Specifically, the threshold is 5.991. In this part, data points for which Mahalanobis distance exceeds the threshold are determined to be outliers, and the results are stored in a Boolean variable called isOutlier. In this variable, outliers are recorded as true and a normal data point as false. The Mahalanobis distance for each data point and the result of the outlier determination are then added to the data frame. Let's create a straight plot to visually compare the Mahalanobis distance between outliers and normal data points. However, no data points were determined as outliers, so all data points were shown as normal data points. In other words, this figure shows that, based on the normal Mahalanobis distance, no data points would be considered outliers. Although there is some variation in the Mahalanobis distance, outliers are unlikely to be detected because the distance is calculated including outliers. This is the scatter plot we created before. The two variables seem to be correlated, but the relationship is not perfectly linear, and there is some degree of variation. However, since the usual Mahalanobis distance is calculated including outliers, outliers seem to be hard to detect. Now, let's implement outlier detection using MCD method. Create again a dataset with only two variables as large X. Next, apply mean_cov_det class and the fit method to the dataset X to compute a robust covariance matrix and a robust mean. The results are stored in a variable named MCD. Using the result of this calculation, compute the Mahalanobis distance. And set the threshold value as before. As before, outliers are detected based on a threshold value. Here, outliers are recorded as true and a normal data point as false. Then, the Mahalanobis distance based on MCD and the result of the outlier determination are added as columns of the data frame. Let's create a straight plot. This time, we see that outliers are detected. We can see that data points whose Mahalanobis distance exceeds a certain level are considered as outliers. Let's create a scatter plot to visualize the result. Outliers are represented as orange dots, and other data points are blue dots. We can see that the data points with high color intensity compared to alcohol values are detected as outliers. If we exclude these outliers and look only at the blue data points, we can visually see that the two variables are more strongly correlated than the entire data. Thus, by using MCD method, we can detect outliers that cannot be detected by the usual Mahalanobis distance. Thank you for watching. If you have any questions, feel free to ask in the comments. Your feedback is always appreciated.